Hello, AB Calculus. Here we are for the final topic of the year. Woo woo! So, strange that it's on a video, but that's all right. I'm in Georgia visiting my son who goes to UGA, so thank you for your attention to the video. So this is cross sections. This is one of my favorite topics in calculus. Cross sections. Okay, and this is a volume. But we're not revolving, okay? We're just going to be accumulating cross sections. And actually, I'm going to pause and go get you a little visual, so hold please. Okay, I'm back with a little model. So in years past, we've done these projects. We haven't done it in the past 2 years because of COVID and such. And I'm not sure we'll do them this year after the AP exam. We might, or we may introduce you guys to polar, since you have to know how to work with polar coordinates in BC, but to be determined. All right, so what's a cross section? So it's a volume, so it's a 3D figure, but it's not revolved. Basically, you have the area of interest is your floor, if you will. So you're going to have an area of interest that we would revolve if it were a volume of revolution, but this is going to be the floor or the bottom, the base, if you will, of our cross section. And then we're going to raise certain shapes from that floor. So for example, you see this? This is the little project. So this is a cross section right here. Let's see how well you guys see it best. The base of it is this shape, okay? So this is the base. The base is a parabola. So there's your parabola. And then that's the base of it. And then on that parabola, we've raised cross sections of squares. So all of these squares get accumulated, and it creates this sort of figure. Okay, so it's got a base, that's a parabola, and along the parabola, you're just accumulating these squares. And the integral, of course, will do that. Okay, so here's another one. This one has cross sections that are triangles. This is like equilateral triangles. And this base looks like it might be an ellipse. Okay, so you've got this ellipse is your base. That's the area we're going to graph. And then from that, you're going to raise up these equilateral triangles. So you've got a base, and you've got a shape. Okay, one more here. Let's see. I have thousands of these things, it feels like. This one looks like there's some names on here. A bottom that is a circular base. So graph a circle. And then looks like we've got isosceles right triangles here with a leg down. So this would be an isosceles right. That's a right triangle with a leg down. And then those just get accumulated on that base. And this is a volume. And so the integral will calculate this. So there you go. All right. So with the disk method, you can find the volume of a solid having a circular cross section. And this is revolved, so it makes that circle. Since it's revolved, it makes that circle. And so how did we navigate the disk method? We had pi r squared. We had the formula. So we can do this with any shape. With revolution, because of the revolving, it's going to be a circle. But if we don't revolve, we can still create a shape that's three-dimensional with any shape. We just have to raise it from that floor. Instead of revolving the floor, we have to raise it. So we can do this with respect to x. Sorry, this is smeared. We can do an area with respect to x of any shape. Okay, so you would just integrate left to right, a of x dx. And those would have the cross sections perpendicular to the x-axis. So here's x and y. So here's some floor, right? Here's some floor right here, and it looks like we're raising rectangles for this one. Here's a rectangle. Here's the end slice there of a rectangle. So this would be a dx situation. And then here's this floor, this shape, this parabola, and these rectangles are perpendicular to the y-axis. So this would be integrating bottom to top of ay dy. Okay, so there's the end, and these are these cross sections. So this would be a dy situation. Okay, so let's go down to our prompt here. The solid lies between the planes perpendicular to the x-axis. Okay, so that's huge. So now we know this is a dx world. This is x world. So the bounds are left and right. We have some symmetry here, so note that. Cross sections perpendicular to the x-axis between these planes run from this graph to this graph. Cross sections are squares with bases in the x-y plane. You can find the volume of the solid. So really, it probably might not read like this. It might more just read that you have this, it might just give you this equation. So, note if I had plus or minus root 9 minus x squared and squared both sides, y squared equals plus or minus would be positive 9x squared. You can see that you certainly get this, and that is just a circle of radius 3. Okay, and so there it is graphed. I'm going to graph it. I don't really like it at a slant, so I'm going to graph it here. All right, so we're out 3, negative 3, negative 3, 3. There's my circle. That's my floor. And we're raising squares. So square, here's a representative square. Okay, so there's that. And let me draw that a little bit. Try to give it a little 3 dimension. So there's that. And we're going to have infinite squares, right? So infinite squares. So this is fairly similar to this one, infinite squares, except this has a base of a parabola, and this one here has a base of a circle. But the infinite squares are going to gather like this with a circular base. Okay. So here we go. So we know the area of a square, side square. Okay, and so in terms of x, we had to figure out how to represent this side. Okay. So the side of a square is, well, this distance, x-axis up. Put your finger, or not your finger, your pin on the x-axis up. This distance is defined by y equals root 9 minus x squared. And this distance here, well, I think my arrow a little better here. This distance to here goes from the x-axis to here, and so that's a distance, or it's defined by 9 minus x squared. Well, that total distance would be top minus bottom, top minus bottom, top minus bottom. So top minus minus, this total distance, this side would be 2, 9 minus x squared. So you can think about it that way, top minus bottom, or you can just say, okay, well, if that's root, that distance, that segment is defined by root 9 minus x. And this is distance, you could think of distance as being positive, so 2 of those. So that's your side, and so you just cruise over here, and your area is going to be 2, 9 minus x squared, quantity squared. Okay? Yeah, there you go. So we're just going to accumulate all of those, and I'm going to use symmetry. We're going to accumulate all of those. We'll go negative 3 to 3 of side squared dx. Okay, and we're going to use symmetry, so 2. Let's go from 0 to 3 of 4 times 9 minus x squared. Okay, and so 2, let's get the 4 out of there, why not? 8, 0, 3, 9 minus x squared dx. And this is just 8 times 9x minus x, 3 over 3, 0 to 3. So this is 27 minus 27 over 3. This is 8, 27 minus a 9, 8 times 18, which is 1.4 units cubed. Okay, so there you go. All right, so that is a cross-section. There are 2 more examples on the next page. One is circles. So this one's a circle. So this one you could actually do a washer if you wanted to. And then this one is an equilateral triangle. Okay, so when I was learning this, I kind of came up with my own system for dealing with very common cross-sections. So I'm going to show you that using the previous example really quickly, and I also have a separate video on that I made during COVID. So I'm going to get pause the video and get a piece of paper and kind of show you what I call my ratios. Okay, so let's do Muller ratios here. They're not really my ratios, but I kind of came up with this and have shared them with other colleagues. And so on and so forth. So Molar ratio. So let's go back to our square here. Let's go back to our square. Like I said, I have a whole separate video on this that I'll just add for grins, but you may just get it here. Let's go back to our square. Let's take a square. Okay? Let's take a square. And this is side by side. So this is area equals side squared. That is pretty darn easy to deal with. Okay? So that's what we just did here. You know, you got to get your equation right. You probably have to do a plus and a minus and add them together and get that, but you just square it. Okay, so let's take this square and let's say we carved a new shape out of it. Let's say we carved an equilateral triangle out of it. Let's say we did an isosceles triangle with the leg down out of it. Let's say we did an isosceles triangle with the hypotenuse down, or a semicircle. We're just going to kind of carve a new shape, but we're going to always compare it to the square and think about this as a side. Okay, so if we took this to an equilateral triangle, we just took that square that I just drew right there. Let's compare the formulas, okay? So this is an equilateral. So it's Molar ratios to the square, right? You're comparing it to the square. Okay, so if this were equilateral, this would be S, and this would be S, and this would be S. So area would be 1/2 side, base times height, so base is S, so we got to get this height, okay? So this height, this is going to be a 60-degree here, and a 30-degree here. This will be S over 2, and so the ratio to scale up from the smallest side to the middle side is the smallest side, which is S over 2, just looking at that left side, S over 2 times root 3. You guys remember that from geometry and pre-calculus, hopefully. So there's 1/2 base times height. So base is this S, and the height is S over 2 root 3. So this area can be generalized to root 3 over 4 side squared. So as long as you can do a cross-section pretending like it's a square, easy. If it goes to an equilateral triangle, you can just take the area of the square and use the square ratio of root 3 over 4 for an equilateral triangle. That's your ratio for an equilateral triangle, is just root 3 over 4 of just that side squared, that piece of that segment from top to bottom squared. Super easy. Let's do isosceles. Right leg down. So meaning on the, if this were this circle here, leg down meaning that is, base down. And so if we were doing this, this would mean that it looked like that. The leg is down on the area of interest. So it would be like taking that right there. And obviously you can see that's going to cut it in half. But let's just show it in action. So if I went like this, and so this is your circular floor, like if I were to draw them across, it's got to go side to side, sorry. This would be my circular floor. And, obviously would be perpendicular to the axis, but it would be raising, like this, okay? And so that's what I mean when I say leg down. That's the part that's going from curve to curve. Anyway, but just to develop the ratios, this would be side, okay? And this would be side, and this would be side root 2, who cares? We just want this area, 1/2 base times height. So how does that compare to the square? The ratio is 1/2. So if the problem reads, you have an isosceles, right, with the leg down, you can just pretend it's a square and take half of that. So for all of these problems, so the answer there would be 72 for this one. If it had said isosceles right leg down, I would have said 72. And if it had said equilateral, I would have taken this and multiplied it by root 3 over 4. Two more here. Isosceles. The only reason I show you these is these problems come up a lot. Isosceles right hypotenuse down. Okay, so this is going to look like here. So this is side. Again, this is going to be top curve, bottom curve, whatever. But this, this is 45, 45. This would be over root 2, and so 1/2 S over root 2 s over root 2. This, in comparison to a square, is 1/4 s squared. So that ratio is 1/4. And then another common one is your semicircle. So there's s. Okay, and so what's this formula? Well, it's 1/2 pi r squared. Okay, so r is going to be half of s. And so that is 1/2 pi s squared over 4. And so what is that in comparison to the square? Pi over 8 s squared. So the ratio for a semicircle is pi over 8. Okay, and then if they have a rectangle, rectangle doesn't have a set formula, but if it's a rectangle, it'll read something like the height is 2 times the base. So that ratio would be 2, because the base would be s, and then if the height is 2 times that, that'd be 2s times s is 2s squared. It might say the height is 3 times the base. So that ratio would be 3. It might say that the height is half of the base. So that ratio in comparison to a square would be 1/2. So rectangle you can manage pretty easily. But again, big picture, it's just the area formula described correctly by the curves, behind the interval. All right, so let's get back to the notes. 2 more problems. A solid has its base to the parabola x equal y squared, and all cross sections are circles. So this one we could use disk, but we're going to use cross sections, whose diameter is the width of the parabola. Find the volume of the solid between x equal to 0 and x equal to 4. All right, so let's just draw this out. We've got x equal to y squared. So y is equal to plus or minus root x. Okay, so there's that. That's y equal to root x. That's y equal to negative root x. We're going to 4. So there's my floor of the solid. Okay, so this is 4, 2, and this is 4, negative 2. Okay, and we're doing circles. So this is going to kind of come above and below them. So that we've got the diameter is the width of the parabola. So that's the diameter. So the circle's going up, and then also going kind of underneath, if you will. You can visualize that. So that you have some you have a cross section that goes under, it goes to the basement. You have the floor, and then so some of the circle's above and some is below. All right, so a circle has an area of pi r squared, and this cross section, it said it's the width of the parabola, so it's perpendicular to x, so this is dx. And we just got to write that radius in terms of x. And so that radius, we're going here to here, so we're going 0 to 4. And we just got to do pi r squared. All right, and so this radius then here is just going to be from here to here, either direction. Radius is a unit of measure that's distance, so it's just root x. This one's pretty easy, if you can see it, because I've got it covered. Okay, so we're just pi that out. Okay, and you can see this is basically a disk situation. All right, so pi x squared over 2, 0 to 4, and that's just going to be 8 pi units cubed. Okay, last one here. Base of a solid is the disk. Okay, so there you go. We got a circle. The cross sections by the planes perpendicular to the y-axis. Between y equal to negative 3 and 3 are equilateral triangles. I'm thinking symmetry. Find the volume of the solid. Okay, so we know this is 1/2 base times height, but I'm going to use my ratio. Okay, I'm going to use my ratio. I'm going to also use symmetry. So negative 3 to 3. We're basically going to be just using our ratio is root 3 over 4 when we deal with equilateral triangles of side squared. Right? And this is dy, so we got to write the s in terms of y. All right, so let's do that. All right, let's do that. So this is going to be basically, you know, here's this base. If this were a square, that would be the base of this square. That we're carving out that equilateral, so I'm using root 3 over 4. All right, so let's define this. So this would be x equals, going perpendicular to y. So this would be x equals 9 minus y squared. And over here, that would be that curve. And then the curve here would be x equals negative 9 minus y squared. Either way, that side, that base, would be 2 root 9 minus y squared. Right, minus minus left, or you can just think of it as two of them. Okay, so area in terms of y is going to be this root 3 over 4, 2 root 9 minus y squared. So I'm going to use symmetry. Okay, there we go. So that's what I'm going to do. So again, if you forget the ratios or you don't like the ratios, you can always just say, okay, well, you can still define that base and then bring this triangle out and say, well, this whole distance is 2 9 minus y squared. So if I had to get area, I would do 1/2 base, which would be 2 root 9 minus y squared. That's that whole distance. And then if I had to configure this height using special right triangles, I would just use the fact that this is root 9 minus y squared. And how do we go there? We multiply by root 3. Scale up on that 30, 60, 90 situation. So that root 3 would come in here, 9 minus y squared, okay? 1/2 base times height there. And we're going to get the same result. So it doesn't look like it right now because I haven't simplified this, but this would be root 3 here, okay? And then this root 9 times root 9 would be 9 minus y squared. Okay, so just hold, hold that thought. And when I move over here, this 2 is for symmetry. Okay, and when I square all this, the 2 is going to square to the 4, which is going to cancel. Root 3 is just here. So this will cancel with that, right? And then that will release 9 minus y squared. So same thing. Same thing. Okay, so let's get the root 3 out. 2 root 3. And let's go ahead and integrate because I'm out of room. So 9 y minus y cubed over 3 from 0 to 3. 2 root 3 times 27 minus 27 over 3, which is 9. It's 18. So 36 root 3 units cubed. Okay, so there you go. We're done, folks. Should I drop the mic? Drop the mic. Oh, that's my mic. So that was meant to be funny. We did it. All right. So there you go. There's your notes. There's some ratios. I'll throw an Edpuzzle on this just for grins, and I'll also upload me going through the cross section ratios that I kind of came up with when I was learning this. And when I went back to teaching, I had to dig deep and try to remember those, but it was all still there somewhere. Anyway, so I will see you guys when I get back. And until then, be well. All right. Thanks, guys. Bye.